Dear colleagues, I'm Gleb Rudnev from YaCu company, where we establish unmanned logistical cargo delivery platform, and we decided to run a solution of the neural network in parallel. First of all, open worlds, open set problem, open set recognition is a problem which was revealed at neuron networks also in real time. There can be a lot of noise present, there can be a lot of interference, and they are unlimited in their variety. This state of affairs causes quite a lot of unpredictable behaviors. The simplest example here would be sending feed of letters that are handwritten. TensorFlow is showing you the output, like for example B, J, and Y that are handwritten, and they are recognized as predicted with a high prediction and high softmax probability. We have two known classes, KK class, KU class, and UK class and UU class. So everyone has been taking the effects into account, can give a go and study these four classes and see how it is showing agnostophobia. Other methods would be identifying and recognizing road signs, human faces, etc. For example, you just need to point out unknown faces, which is one of the most difficult tasks. There were some other issues occurring a few years ago that are enough to create this agnostophobia and leads to skipping. For example, even numbers and odd numbers, like the slide on the right, was taken for numbers, and among the objects, the left ones have been wrongly detected. And we come up with the two main groups, enhancing of background of garbage classes, for example, and the thresholding response. Threshold response is one of the simplest, setting negative parameters to networks, but we also show positive responses to known classes on the trained network. These are not fighting agnostophobia, but they are offering existing solutions, and they're not responsible for the second problem of networks. Spreading of the real classes is chaotic. The classes should not be creating such objects in space. Check out this slide. This is one of the methods shown with the known classes 1, 3, 4, 5, and 9, KKC 0, 2, 6, 7, 9. Unknown class, handwritten letters, known unknown class, KUC. There are many subclasses in the stochastic form. Then the thing is that the traditional approach to neural networks, which is based upon the optimization of the linear classificators, is not studying the features of the classes, but it studies the separators, studies what separates them. Here, if we would like to tune the scale 1, 2, 3, takes into account all of the fields, and there are two features. First, we identify unknown fields, which is not provided with the standard gradient descent class, but maybe it will be singled out with some in-depth features. And there is quite a lot of variability. Agnostophobia battling methods will have to overcome these two things. So it seems like the neural network's pathway is more or less clear. With the ASR, we just need to go away with the separators, and we'll need to end up with the other ones. So the next slide is showing real classes that are multiples of compact subclasses, and the closer these separators are to the real ones, the less agnostophobia we expect from the network, and we can store, use and reuse useful separators. But it's not so cloudless here. The selection of such shells requires quite a lot of computational power. It's quite complicated. We've been able to design this network based upon these shell separators, and currently it's the result of heuristics, and the mathematical approach will yet have to be done. So let's consider this network and the functions identifying the classes of the binary type, and we call it neuron. It's made up of sub-functions that create separators of subclasses and modernize them. We call them hypotheses, and this does not require deeper layers. We have the disjunction of the neurons. In the second approximation, we can compare the weighted sum, especially when it does not require very high precision. And the output of hypothesis happens when it gets inside the separators in hypothesis. Here it becomes quite obvious when this goes to looking for separators that match quite well with the shells. But the selection in this space will have to be done in very inventive fashion, and the use of the rectangular separators will help us run this optimization. Down there on the left, a formula is shown with the indexes m, for example, the change of the space. All of these are synonyms, and there are some dense separation shown on the right, which will help us bring together the shells. And we need to quantum the fields and make it easier. So we haven't found any other ways rather than evolutionary algorithm. But as compared to the real genetic approach, we just need to work out a multitude of algorithms, and we can perceive them as those that are adjustable, as an adjustable genetic code. And here are a few features and biases. The first one of a distinctive species is a current predecessor, point of known class. It means supervised learning. Creating new distinct species should never be stopped. Each of the captured precedents has to be hybridized with the future ones, creating childs, and it should be generating new details. And let us just take a look at the simplified fragment, simple frame of evolution. Here is the X0 captured by neuron, and the predecessor S1 is created. Then they are spliced, reward, no success, miss, etc., ending up with S5 and S6s in the end. And the ratio of the rectangular separators and the shells that are contoured in red shown on the slide, and the evolution process can be considered as the volume of the precedent by the continuous splicing, increasing the sensitivity. This is shown on the graph here with blue bar, the blue ones showing the sensitivity, and the red stand for error level. And if we consider the results and statistics, here is this data set used here, 3 levels, and on every neuron After 3-5 evolutions, we have 360 hypotheses developing. It is illustrated here, this stable hypothesis. For example, red color on black, background white are pixels, and their brightness may reach any value. And the key thing is the background, the contour, the spreading of the pixels. But the actual marks play secondary role. And on the right-hand side, we have typical recognition statistics, and ultimately our network became quite non-susceptible to not useful classes and has recognized only half of the useful classes, with the errors reaching approximately 25%. We continue this technology research. We take into account open world, and we know that these requires admitting lots of difficulties, and the biggest difficulty would be hard computing and taking a lot of memory, and it's sensitive. And I would like to say that the rectangular separators are very sensitive, and the evolution reduces as we have correlation in place. So we'll have to use convolutional changes of space, or move into other forms of shell separators. But the first approach is preferable. In the end, we hope that developing the methods of research of neural networks at these separators, if you like, will find the response with experts, and may be interesting to those of you who are experts. Thank you very much. I'm done. Maybe you should ask me some questions.